Welcome to the next lecture of power electric circuit analysis. We have to see power factor correction today. In last lecture we have seen some examples of complex power and details about what complex power is. Today we are going to see power factor correction. The most most of the domestic loads we usually face are inductive in nature. For example, we have washing machines, we have air conditioners, we have different appliances in our kitchens, and various examples can be quoted from our nearby. All these appliances are inductive in nature and they do have a lagging power factor. This lagging power factor demands an extra reactive power from the grid, and the nature of the electric power appliances cannot be changed. It will remain as they are because there need to be a motor windings and coils in order to get the motor action done. However, we can improve the power factor of our appliances, and in this lecture we are going to see how this will happen. This whole phenomena of correcting the power factor or improving the power factor of our load is called power factor correction. What we actually see is that the load's power factor is usually, in case of inductive loads, like we can see in this circuit, part of the circuit on the left side, it has inductive element along with some resistive portion, and the current IL flows through it. From the phasor diagram, what we see is if we keep the voltage as a reference, then the current lags behind the voltage, and this amount of current will be flowing through the load. However, if we connect some shunt capacitor, a capacitor in parallel to this load, this will change the amount of current drawn from the source. This current I will be changed a little bit, and what might be the reason for this? The current flowing through this capacitor is 90 degree with respect to the voltage across this capacitor. Because this is pure capacitor, we have, in this case, the current and voltage are not 90 degree apart because there was some resistive portion connected in series with the resistance. That is why this current IL is not at 90 degree from this voltage. However, the current of the capacitor and the capacitor voltage would be at 90 degrees from each other because it is pure capacitor. And secondly, the voltage across this capacitor and this RL portion would be same as V because all these elements are connected in parallel. R and L is connected in parallel to the C. Therefore, the current and voltage will have 90 degree phase difference in case of capacitor. Keeping in view this thing, the resultant current I is actually sum of IL and IC. This is the vectorial sum of IL and IC. So initially we had this IL current. Now this phasor current IC should be added, and we can add two vectors like head to tail rule. So we place this IC vector at the head of this IL vector, and the resultant vector would be I. We can see that the phase angle between voltage and current was theta 1 in previous case, whereas it's now theta 2 in after connection of this capacitor in parallel to this RL circuit, resulting in the reduction in the phase angle theta 2 from theta 1 to theta 2 now. Keep in mind here the supply current was IL, which was also flowing through the load, However, in this case the supply current is I, so we can easily distinguish between these two. Now the supply is facing the phase power factor corresponding to this theta 2 instead of this theta 1 in previous case. So we can see that in this case the load current will be reduced a little bit, so the power delivered by the load, the complex power delivered by the source, would be reduced a little bit also. We also notice from the magnitude of the vectors that with the same supplied voltage, the circuit in figure A draws a larger current IL as compared to the current I in case of figure B. So in this case we are now delivering lesser power for similar amount of load. The power companies charge more for the larger current because they result in increased power losses. Because the large current is flowing over the lines, and lines have some resistive as well as inductive portions, therefore this will incur more losses on the lines in case of larger current. So due to this, power companies only allow certain limited power factor. If the power factor goes below this, then we will not be able to see the power companies will not allow this. So from this discussion, what we have seen that a suitable size of capacitor can be helpful in reducing the power losses, in reducing the line currents, and in improving the power factor. Now in this slide we are going to see how this power factor correction works and how can we improve the power factor by choosing a suitably sized capacitor. First of all, for example, we are given with this triangle. This is another method of looking at this power factor correction thing. For example, here we see that from our previous knowledge of power triangle, this axis is related to the real power, this is imaginary power, and because real and imaginary parts are 90° apart, so this is 90° of the angle, and summation of these vectorial summation of these two vectors is S, the complex power. For example, in previous case when only inductive load was in action, the power delivered the complex power drawn from the source was S1, and after correction with some suitably sized capacitor, the reactive power demand from the source is reduced to this level, and now the power drawn from the source is S2. This is from our previous lecture, and if someone has some confusion, he or she may go to the previous lecture for this. Another perspective of the power factor correction is power triangle, and in this triangle we can see that this P is S1 times cos of theta 1, and Q1 is this quantity S1 sine of theta 1, and which can also be written as P times tan of theta 1. Similarly, if some power factor correction is done and reactive power demand is reduced from Q1 to QC due to capacitor, then the Q2 can be written as S2 cos of theta 2. And the reduction in the reactive power is caused by the capacitor, as we have already seen. And this QC amount of power is actually difference of Q1 and Q2. Therefore, we can write this equation, and using this equation 57 and 58, we can write that for Q2 we can also write P times tan of theta 2, right? So we can take P common, and tan of theta 1 minus tan of theta 2 will appear like this. Ultimately, as from our previous knowledge, the reactive power is the voltage square divided by the reactive impedance of the capacitor. As we do in plain resistive circuit, V square upon R. So here we see V square upon X actually, and 1 upon X can be written as omega C, because we used to calculate this reactive impedance of capacitor and inductor already. Xc is minus J upon omega C, and only magnitude can be written as omega C here. So by simply putting the values and manipulating and arranging for capacitance value, we can get P is equal to tan theta 1 minus tan theta 2 upon omega V square RMS. So this is the relationship in equation 60, which gives the actual value of the capacitance required to change the reactive power demand from Q1 to Q2, or changing the power factor angle from theta 1 to theta 2. It should be noted that the average power due to capacitor is 0, because we have seen that we only added the capacitor in parallel, and reactive power absorbed, average power absorbed by the capacitor or pure inductor is equal to 0. So there is no real power dissipated across these elements. So in case of addition of capacitor, the actual amount P remained similar. From here, or in this equation, we took P common because it's same, it's similar. There is no change due to addition of capacitor, because average power dissipated across the capacitor is 0. In this slide number 53, we proceeded with respect to the real power, and for the capacitance for inductive load, where we need to correct the power factor using a capacitor. However, there can be, although it is not very common, but there can be some case in which we have the leading power factor. In that case, we need to add the inductor in parallel to the load for correction of the power factor, and proceeding in a similar way like this one, we can reach this equation number 61 for finding the size of inductor required for the correction of power factor. Here is an example. When connected to 120 volt RMS 60 Hz power line, a load absorbs 4 kilowatt at lagging power factor of 0.8. Find the value of capacitance necessary to raise the power factor to 0.95. So everything is now given. From this power factor, we can calculate theta 1, and the target power factor is 0.95. With this, we can use we can calculate the theta 2. Theta 1 and theta 2 are now known now, and similarly, this is 120 volt RMS 60 Hz, and this is 4 kilowatt. So it's actually active power P. We need to calculate S1 corresponding to this using this relationship, which is 5000 volt ampere. Similarly, at this amount of reactive complex power, the reactive power would be 3000 volt ampere reactive. Moving on, for the next amount of complex power demand, means the amount of complex power corresponding to 0.95 power factor would be this one, from which 1314.4 volt ampere would be the reactive power. So just by correcting the power factor from 0.8 to 0.95, the reactive power demand over the line has reduced from 3000 to 1314, which is considerable amount of reactive power reduction. So in order to calculate the capacitor size, we can proceed. This is the difference in the reactive power demands. Using this relationship we have just derived, we can calculate the amount of capacitance. There is a small note. Capacitors are normally purchased for the voltage ratings because this system is operating at 120 volt RMS. So we need to consider that amount of RMS voltage at which we need to connect this size of capacitor. So when buying the capacitor for this system, we need not only the information about the capacitance but also the voltage rating at which we need to connect it. So it should be a bit higher than the actual voltage it might face under normal circumstances to avoid any damage under some loaded conditions, heavily loaded conditions. For example, the 170 volt is the peak voltage corresponding to 120 volt RMS. We should consider a bit higher, like 200 volt would suffice in our case. Conservation of AC power is our next topic. The conservation of power applies to the AC circuits as well as the DC circuits. From our course on DC analysis, we have seen that the power remains conserved, and it can be proved in number of ways. For example, for parallel connected load, the current I distributes among I1 and I2 to drive the load Z1 and Z2. So from the simple equation, complex power is V times I conjugate. We can write this equation where V times I1 conjugate plus V times I2 conjugate are equal to S1 plus S2, and where S1 and S2 are the complex powers absorbed by Z1 and Z2 respectively. Similarly, for series connected loads, we can have this voltage division, and using the similar relationship we can derive this one: V1 times I hysteric and V2 times I hysteric is equal to S1 plus S2, which ultimately is same as the previous equation. So this shows that the complex power delivered to load Z1 and Z2 will be summed up to get the total complex power delivered by the source. This can be generalized for any number of loads like this one. Similarly, the complex real and reactive power of the sources equal to the respective sum of the complex real and reactive power of the individual loads. There is no loss of active, reactive or complex power in electric circuits, whether AC or DC. And this example actually explains about this conservation of AC power. Figure 11.24 shows a load being fed by the voltage source through a transmission line. The impedance of the line is represented by 4 plus J2 ohm. Find the real power and the reactive power absorbed by the source, by the line and by the load. So we can proceed by the simple calculations. The impedance, total impedance faced by the source is impedance 4 plus J2 plus 15 and minus J10. This is impedance of the line, this is impedance of the load. We have added it up and we reach this value. The current through the source is I is equal to Vs upon Z is equal to 220 volt. RMS is given here and Z we have just calculated here. So the total current I in this circuit is 10.67 angle 22.83. For the source, the complex power is Vs I hysteric, and we need to take the conjugate of this one, and which can easily be taken by just changing the sign of this angle, and Vs is given 220 volt angle 0. So multiplying this is the complex power delivered by the source. Now the power consumed across this line impedance 4 plus J2 ohm would be equal to this one, because the current is similar, it's a series connected circuit. So current is this one and 4 plus J2 ohm can be written like this. Similarly, the complex power absorbed by the line. This is V line. Now we can calculate S line, the complex power absorbed by the line, with this relationship V times I conjugate. This can also be used, but it will result in same equations. And finally, we need to calculate the complex power dissipated across the load. Proceeding in a similar fashion like this one, we need to find the voltage across the load and then need to find the complex power. And from all these relationships, what we see is the complex power supplied is this one, 2163.5 minus J910.8 volt ampere. The real power across the line is 455 watt approximately, and the reactive power is 228 watt var approximately, and it's lagging because it is inductive load. We can identify this with this plus sign, because inductive impedance is positive and capacitive impedance is negative, like this one. This is capacitive in nature. That is why its leading was written here. So the net result would be S is equal to S line plus SL as expected. We can just add this value with this one to get the exactly similar amount of complex power as delivered by the source. So in this case, we can say that the power remains conserved in AC circuits. Here's another example for the parallel connected circuit, and we can proceed in a similar fashion as we did already, and the power will remain conserved here also. Thank you. With this, I close today's lecture. Thank you very much. See you in next lecture.